Log on, tune in, find out. Another good idea from Cambridge.
So, no more words, back to equations. In fact, back to the 19th century. I will endeavor to cover a couple of topics about inverse problems and waves in this talk. And I'll endeavor to make them a little bit more comprehensible than if they had been written in barcode. Okay, so there's a generic way of looking at inverse problems that's been around for a great deal of time, 30 or 40 years, and that's, I think, first popularized by Bill Menke, Albert Tarantola, a number of other people in geophysical inverse problems. There's a model space, which is usually a subset of normed vector space or Banach space, something like that. Data space, so I put space in quotes because usually it isn't an entire vector space that's occupied with these things, and a mapping from the one to the other, which has a bunch of different names depending on which subject you're in. Okay, the forward map is one of its names, and that's what I'll use because I'm used to calling it that. And the problem is to find a model that fits the data. Given the data, of course. And there are all kinds of amendments to this problem. Statistical variations, of course, optimization formulations, which is what I'm going to talk about. But that's the essence of the matter. So I'm going to try to address a couple of issues that arise when F is the forward map of a wave inverse problem of the type that occurs in reflection seismology. So the first issue I will pretty sure I'll get to is what's the relation between the regularity of the model and the regularity of the forward map. Okay. Clearly of interest if you want to use optimization methods, for example, which depend on the regularity. Now that's not even a meaningful question until I make a context for it. What do I mean regularity of M? The second question is a great deal more specific, and that's this: where does space shift imaging which you've heard about several times this week, notably in Fonst and Kroda's talk, come from? And what does it have to do with an inverse problem? Okay, so I think I'll be able to answer those two questions. This first question actually informs some of the habits of thought in reflection seismology that you've heard a number of times throughout the week. I hope that's recognizable. Okay, so I need to put these things in context. There is a third topic I would love to get to, namely what I wrote about in my abstract, how the attempt to solve the seismic inverse problem in the space shift domain leads to a type of tomography, which I think is interesting and new. But I think the chances of my getting to that are so close to zero that we don't even need to talk about it. We'll see. Anyway, so context. There's a lot of context you could bring in, but I will stick with constant density acoustics because it's the simplest one. Okay, so choose units in which density is 1. And then we have a number of pieces of acoustic modeling. Gamma is what I'll call the compliance. That's the reciprocal bulk modulus. It tells you how much change in volume you get for a given change in pressure. Okay, P is excess pressure. V is particle velocity. And these things are related by the acoustic wave equations, which I'll write in this way. And I'll put something there so that we get some motion or another. And then the Newton's law. I should have a Newton law in a talk in this place. Okay. So in order to induce some motion, we need some source of energy into the system, and I'll represent that by right-hand sides in these two wave equations. Okay. And then we would like to define, so this gives us informally a model space. That's all the possible gammas. A data space, which is going to be the restrictions of the pressure to a time interval across a set, and the forward map, which maps gamma to this restriction. Okay, so this is all fairly familiar by now. I don't think I need to draw a geometrical picture. The question is, how do you make sense out of this in such a way that, first of all, f is regular, that is to say has a derivative, maybe a couple, and so that we can see the relationship between the regularity of gamma and the regularity of f. And here's a quick answer. This is a theorem. So there will be theorems, meta-theorems, and pseudo-theorems in this talk. This one's an actual live theorem. It goes back to work of Lyon's. It's an old story. The ideas are really Lyon's, extended in Chris Stolk's thesis to address the regularity issue, and then recently further extended by a couple of the rest of us. So here's the story. Let's actually define M. Let's given a couple of numbers, positive numbers. Let's set M to be the gammas in L infinity of a domain in Rn. I'll say that in a minute. That lie between C lower star, C upper star. So gamma is in R3, omega is in R3. A half space is a good candidate for our purposes. So that's M, and it has the topology of L infinity. So the sup norm is the metric here. D is going to, so Y, what's Y? Y is going to be a subset, a submanifold, open submanifold of dimension 2. Okay, so a surface on which we'll measure things. And let's see, what else do we need to say? F has already been defined. It's just not obvious that it makes sense. So that's the result. If F, the vector FP, FV sits in H2 of 0, 0t with values in L2 of omega fourth. There are 4 components there, right? Then F as defined above is in C1, gamma, D. I didn't tell you exactly what D is. D is just L2 of 0, 1, 0 to T with values in Y. Okay. With values in, in L2 of Y. So there's an actual live regularity theorem, and it doesn't really ask very much of gamma, does it? Very little. You get more derivatives, by the way, for simply the cost of more time derivatives of the right-hand side. So this is great, but not. It gives us something to stand on, but it's not very informative. So I want to give a simple example that shows that there must be a great deal more going on than this. Very simple. Let's take the case rather than the 3D case, which I wrote out here. This, by the way, is an instance of a whole family of similar theorems. This is just itself a special case. So let's take dimension 1 instead, because it's easy to solve one-dimensional problems by hand. And let's take for M, gamma is in L infinity of R, for which gamma is constant for Z less than 0, and of course positive. So let's just say log gamma, L infinity of R. And D is just going to be L2 of the real line. That's all. And we will solve the problem. dp t gamma minus d dz, and dv dt is minus dp dz. With the condition that p of zt is a wave moving to the right at large negative times. And correspondingly, v has to be 1 over c times f t minus z over c. This is for z and t less than 0. Here c is simply the square root of 1 over gamma. That's the wave velocity of this problem. Okay, so this isn't quite the form of that problem with energy entering through right-hand sides, but it's really easy to turn it into that problem. No problem at all. And gamma is constant for z less than 0, so that's C here is, this really is a solution for z and t less than 0, and then, it does whatever it does. So let's, first of all, then f, what's f? I have to tell you what f is. F of gamma is a function L2 of R, and it's just P of T0. Just take the pressure at time 0. Okay, so first let's look at the case where C is simply constant all over. That's an easy one. So what's f of gamma? You can see it, it's right there. Let's set z equal to 0. That is then globally p for all z and t. So it's just f of t. Well, if we, in other words, here gamma is constant. So if we stick to constant gammas, so on the subspace or the subset on which gamma is constant, f of gamma is very smooth in gamma. It's about as smooth as it could get. The derivative is the zero linear map. Okay, so that's great, excellent. That's part of the message. But then the case 2 is where things get different. Let's suppose that we look at gammas or c's. We might as well look at c, which is c0 for z less than 1 and c1 for z bigger than 1. Then define R to be the usual reflection coefficient. Okay. And then it's an easy calculation to show that f of gamma t is R of R times f of is f of t. There's always f of t plus R of f of t minus 2 over c. So this is the reflected wave that comes from distance 1 away from the origin and bounces back through the origin. It's very easy to calculate p and v for this problem. Now the point is that the derivative of f you can also compute. We can compute it by calculating the system that the derivatives of p and v with respect to gamma satisfy, but in this case we have an explicit formula, so it's easier just to write down what the derivative is. In the direction delta gamma, well, it's just the corresponding to perturbation in delta c over c squared times r times f prime of t minus 2 over c plus the derivative with respect to gamma of r. This tells you a couple of things. It tells you that we really had to have some derivatives of f in order for, of the right-hand side, in order for capital F to have even a Gateau derivative, a directional derivative. That's part of what the statement of this theorem. It turns out you need a little bit more than that, more than just one derivative in order for there to be a Fauché derivative. But that's what it says. So there's a link between sort of a sharp link between the regularity of the right-hand side and the regularity of F. And the second thing this tells you is that there's a link between the regularity of gamma, or the coefficients, and the regularity of F. And I'll just say that there are more demanding conditions on the data for F to be regular with irregular coefficients. We had the first case, we had absolute smoothness if we kept gamma constant. The second case, gamma had a discontinuity, and it turned out that the data had to be regular. In the first case, F gave you something perfectly reasonable in L2 and in the data space, even if little f was merely square integrable. In the second case, the irregularity of the coefficient forced a condition on the data. This gives rise to, here comes a meta theorem. This is not really a theorem. General conjecture that F is more regular in problems of this type when the reference point at which you examine the derivative is itself regular. So the first order Taylor polynomial is closer to f when you examine the behavior of f around a smooth point. Okay. And there's another issue that isn't obvious from these two examples, but if we consider the directions, it turns out to be also advantageous that the directions be oscillatory in some sense. Now this is really meta because I've used all sorts of value words which don't have a precise meaning. But that's nonetheless what guides, it's a reasonable guide to thinking about this subject, and it's why when you hear the mathematicians in this workshop talk about the seismic inverse problem, they almost invariably mandate that the background velocities or whatever's models in the linearized problems that have played such a big role this week are smooth. Okay, so I got through the first point. The second point I have about 3 minutes to tell you about, and it has to do with, it's simply out of the question. That's what it is. It's not going to happen. There's a lot of structure here. I'll just say this.
Sorry, but what kind of, I mean, you said you indicate this works for seismic somehow. I mean, what kind of range of inverse problems are you claiming that it?
This is for F related to inverse problems and waves, like the seismic problem.
I'm just trying to distinguish it from the Calderon problem that's analytic.
Yeah, no, this is like the acoustic problem. So if you replace acoustics by elasticity, for example, elastodynamics, same story. For problems, for wave problems. That's the distinction, not for statics problems. Okay. So the space shift business, the story there that I would have liked to have told you is simply that the concept is related to what I call model extensions. This is just a systematic way of accounting for the added parameters, the space shift. Unfortunately, it would take me more time than I have to go through all the calculations. I'll just say that the basic structure is that there is a bigger extended model space depending on additional parameters in all of these constructions, including the space shift construction. In the space shift construction, the added parameter is the space shift, unsurprisingly. And an extension operator, well, we know from the last talk that the extension operator is called E. So the modeling operator takes or forward map takes the model space to the data space. An extension is a map from the extended model space to the data space that makes that diagram commute. You can go around either way. And the space shift constructions that you've seen from Fonst and Kruda and so on have to do with linearization, so we would have to talk about how this structure works with linearization. And rather than do that, I will simply refer you to a paper and call the proceeding to a halt. In geophysical prospecting in 2008, I gave a description of this business, and you'll see, if you take a look there, the very equations that you saw in Fon's talk and earlier in the week in WIMS concerning space shift imaging, and you'll see how it comes from posing the inverse problem for an extended model rather than for the original model. And with that, I think I'll wrap things up.
You don't want to take any questions before I...
Oh, certainly.
Let's give him it. So I think Bill's not going to be let off without a couple of questions. There must be from you experts in the audience. No, you're going to give him an easy ride?
I was going to ask about the annihilators in the abstract.
The annihilators, I was hoping someone would. That's another piece of this diagram. An annihilator is just another map from the extended model space to yet another Banach space of some kind, whose kernel is the image of the extension operator, making this a short exact sequence. So, in other words, we will look for all of this business about space shifts and the Bohr parameters and so on as a way of dodging around the sort of stiffness of wave inverse problems by throwing in a whole bunch of additional degrees of freedom. And then you have to get rid of them. Well, you get rid of them by seeing that you're in fact in the range of E. That E is really sort of the identity. It embeds the original model space in this bigger one. And you want to eventually solve the inverse problem in the original model space. So you need to solve the extended one with a solution that's in the range of E. Unfortunately, it's really hard to tell if you're in the range of something. To say that you're in the range of something is an existence statement. You have to say, well, there is something that maps to it, right? That's hard. It's much easier to apply an operator and see if you get 0. So the annihilator is this other operator whose kernel is the range of E, and it's used precisely to test or quality control, if you will, the extended solution.
Would it be appropriate to mention that in three-dimensional X-ray tomography, the extended model space would be measuring a 4D set of rays, and then W would be John's operator?
That's right. It turns out that this subject turns up in Fritz John's paper of 1938. And Fritz John identifies some annihilators not for seismic problems, but for integral operators over various families of conic sections, which are, of course, related to solving wave equations, oddly enough. Yeah.
Right, so, well, before I hand the chair back to Bill, give Bill a clap for his talk. Just one remark, I mean, I think one of us ought to represent everybody, so we'll thank the two Bills. I think it's Bill Symes and Bill Lionheart, who essentially organised our splendid interdisciplinary, multidisciplinary workshop this week. So let's give them both.